Assalamualaikum warahmatullahi wabarakatuh and hello everyone. In this video, we're going to discuss our week 3 hour 3 tutorial for both NFTF and FTF questions for chapter 2 thermochemistry. So, the learning objective for NFTF questions is to perform calculations by referring to the enthalpy change and thermochemical equations. So, given to you information regarding a sample of carbon, which is 2.4 gram, is burnt in a calorimeter. So you have the keyword here is burnt in a calorimeter without the questions telling you what kind of calorimeter is this. So whenever you have combustion reactions, just go for the bomb calorimeter. Extra information given is about delta H formations of carbon dioxide, which is negative 394 kilojoule per mole. So we know that definitions of enthalpy of formations is heat change. So heat change, it can be either positive or negative. So you can simply ignore the negative sign when doing the calculations, as long as we know that this reaction is going to release heat. Alright, so information is given about heat capacity, which is 10 kilojoule per degree Celsius. Now the questions wants you to find the temperature change. So temperature change of the calorimeter. So before we start doing the calculations, we need to first write the thermochemical equations for these reactions. In order to form carbon dioxide, we need to have carbon in its most stable state, which is solid, react with oxygen since this is a combustion reactions in gaseous states to give you 1 mole of carbon dioxide in gaseous states. Okay, don't forget the delta H because it is part of the thermochemical equations, which in this case the value is negative 394 kilojoule per mole. So we know that this delta H tells that 1 mole of carbon dioxide releases 394 kilojoule energy. So now we only have 2.4 gram of carbon. We want to find how many energy will be released from this number of mole of carbon. So we need to first calculate the number of mole for this carbon. So since we are given mass, we're going to use this formula. Mole is equal to mass over molar mass. So our mass is 2.4 gram. Molar mass of carbon is 12. So we're going to get 0.2 mole carbon. You can also use formula of delta H is equal to Q reactions over N to find the heat released or absorbed for this number of mole. But it is suggested for you to use stoichiometry, as we've already learned about this in semester 1. So we know 1 mole of C releases 394 kilojoule. So how much energy will be released from 0.2 mole of carbon? So we're gonna cross multiply this value. So you're gonna get a value of 78.8 kilojoule. So this is gonna be our Q reactions. This is our Q reaction, 78.8 kilojoule. Now the questions ask you to calculate delta T. So if you look at these questions, you're given informations only about the calorimeter, no information regarding water. So you need to know some of the setup of this calorimeter already include the water as part of its calorimeter. So we can simply ignore the Q water in your bomb calorimeter formula. So we're gonna calculate it by our Q reactions is equal to Q calorimeter, where our Q calorimeter now is C delta T. We have the value of Q, we have the value of C. Now we want to calculate the delta T. So our delta T, we have 78.8 kilojoule divided by 10 kilojoule per degree Celsius. Lastly, you're going to get temperature change of 7.88 degrees Celsius. So this is our temperature change for these combustion reactions. Let's proceed to question face-to-face. So the learning objective going to be calculate the heat change in constant pressure calorimeter. So constant pressure calorimeter, also known as coffee cup calorimeter or simple calorimeter, all have the same setup, where we have styrofoam cup and then we put a lid on there and we insert a thermometer and also a stirrer. Then we're going to react two types of solutions together. Now let's look at these questions. We have 200 ml of 1 molar sodium hydroxide, so we have base in here, and then we're going to react them with 150 ml of HCl. So once you've got this type of questions, you need to take out the thermochemical equations. So we're going to have sodium hydroxide in aqueous states react with hydrochloric acid. So since this is reactions of acid and base, we're going to do the neutralizations, where we're going to get sodium chloride acid salts and water. So we want to find the enthalpy of neutralizations in kilojoule per mole. The temperature rose from 25 degrees Celsius to 30 degrees Celsius, indicates that this is your delta T. Then the questions ask you to calculate the heat of neutralization. So we want to find the heat of neutralizations in here. But please remember that these thermochemical equations only gives information regarding 1 mole. But are we certain that our solutions will give exactly 1 mole of water? So we need to check it since we have different volume of solutions being given. So we need to calculate the number of mole for both solutions since this is solution. So we're going to use formula of mole is equal to mv over 1000. So our molarity is 1. Our volume of sodium hydroxide is 200 divided by 1000 because we want to change it to liter. Then lastly, we're going to get 0.2 mole sodium hydroxide. While for HCl, we're going to have exactly the same formula, but this time around, our volume is only 150. So, substitute this value into the formula. You will get 0.15 mole. So if we do a bit of stoichiometry here, 1 mole of sodium hydroxide react with 1 mole of HCl to form 1 mole of water. So we can check which of these two reactants will be the limiting reactants. So now we have 1 mole of HCl react with 1 mole of sodium hydroxide. Therefore, 0.15 mole HCl must react with 0.15 mole sodium hydroxide. So if we compare the number of mole needed for these reactions with the number of mole provided, we can see that sodium hydroxide is in excess states. Therefore, it can be concluded that HCl is the limiting reactant. So we're going to use this 0.15 mole as the number of mole to calculate the delta H neutralizations. Since our questions didn't give any information regarding calorimeter, therefore we're going to conclude that our Q reactions is solely based on the Q solutions. So we know that our Q solutions are going to be MC delta T. So MC delta T with respect to the solutions involved. Our mass now is simply adding these two values, 200 ml and also 150 ml. And since they already tells us that the density is 1 gram per ml, we can cancel out the ml and this total volume will immediately become the total mass. So we have 350 gram times with our specific heat capacity is 4.18 joule per gram per degree Celsius. And lastly, our temperature change is from 25 to 30 degrees Celsius. So the difference between these temperature is only 5 degrees Celsius. 5 degrees Celsius. So once we calculate this value by using calculator, then we're going to get value of 7315 joule. But this is not the final answer for this question since they ask for enthalpy of neutralizations. So we need to combine Q reactions and also number of mole to finally get the enthalpy of neutralizations. Number of mole of HCl is equal to number of mole of sodium hydroxide, also the same as water, which is 0.15 mole. Because we are talking about enthalpy of neutralizations, means we want to focus only on the water. So we are going to relate the number of mole for water with the heat release. So 0.15 mole of water is formed from the 7315 joule of heat. Now we want to know how much heat is released to form 1 mole of water. So if we cross multiply this value, we're gonna get enthalpy of neutralizations of 48760 joule. Okay, since enthalpy of neutralization usually expressed as kilojoule per mole, now we're going to change this to kilojoules. So 1, 2, 3. Therefore, our final conclusions is heat of neutralizations is 48.76 kilojoule per mole. Okay, so this is the final answer for these questions. Now, let's proceed to question 2 for this face-to-face tutorial. A quantity of 85 ml of 0.900 molar HCl is mixed with 50 ml of 0.0900 molar potassium hydroxide. So we have acid and base. Again, we're going to do the neutralization reactions. Already given to you hint about the constant pressure calorimeter, means the coffee cup calorimeter. that has a heat capacity of 325 joule per degree Celsius. If the initial temperatures of both solutions are the same at 18.24 degrees Celsius, so this is your T1, the initial temperature, calculate the final temperature. So this time around, we don't want to find delta T, we want to find only T2 of the mixed solutions. Given to you informations about heat of neutralization, which is 56.2 kilojoule per mole. Assume the density and specific heat of solutions are the same as those for water, means density is 1 gram per mil, specific heat capacity is 4.18 joule per gram per degree Celsius. So, we've got all the information that we need to answer these questions. So, we'll start with the thermochemical equations. So, the thermochemical equations gonna be HCl aqueous react with potassium hydroxide aqueous to give you KCl as your salt plus with water. So make sure that your thermochemical equations is already balanced, and your delta H gonna be negative 56.2 kilojoule per mole. Okay. So you want to find the temperature too, means we need to first find the delta T. So delta T comes from the Q reaction. So in order for you to get the Q reaction, we need to first find the Q reactions from heat of neutralizations. So we're going to do exactly the same steps as in previous questions. We will find the number of mole for both HCl and also potassium hydroxide and determine which of those will be the limiting reactant. Okay, so for number of mole of HCl, we have our molarity of 0.900 times with volume of 85.0 divided by thousands. You'll get number of mole of HCl as 0.0765 mole. So this is the one being provided by these reactions. And then we're going to calculate the number of mole for potassium hydroxide. It has the same molarity as for HCl, but with different volume, which is 50. Okay, so we have 50 ml divided by 1000. Your number of mole for KOH would be 0.045 mole. Okay, so now we're gonna do some stoichiometry to compare these two values. Let's say we take this small number in here to compare with. So we have 1 mole KOH react with 1 mole HCl. If we have 0.045 mole KOH, we also need 0.045 mole of HCl. Okay, so the one that is needed in the reactions is 0.45 mole HCl, but then the one is provided is 0.0765. So we could see that this HCl is an excess reactant, means that our KOH gonna be the limiting reactant. So this is our limiting reactant. We're going to use this number of mole to calculate the Q reactions. From the balance equations, we know that the number of mole for HCl is equal to number of mole of QOH equal to number of mole of water. From the enthalpy of neutralizations, which is 56.2 kilojoule, we know that 1 mole of H2O formed releases 56.2 kilojoule. Now we are going to change it to joule per mole. Then we're going to have 56 to 100 joule. If we have 0.05 mole H2O, how much heat will be released? So if we cross multiply this value, we're going to get 2529 joule. So this is going to be our Q reactions. So we want to find the final temperature. Now we're going to substitute this Q reactions value into the formula of constant pressure calorimeter, where we have Q reactions equal to Q solutions plus Q calorimeter. Since the questions already give information regarding both solution and calorimeter, then we need to include both factors in the calculations. So our Q reaction is going to be MC small c delta T plus capital C delta T. So we're going to first find this delta T and substitute everything else. So our Q reactions is 2529. Our mass is 85 gram plus 50 grams, so we're going to get 135 gram. Our small c is 4.18, and then we have delta T. Same goes to our capital C. Capital C already been given, which is 325. Then we have delta T. So take this delta T, put aside. So we're going to calculate this delta T. So the final answer for this, so our delta T gonna be 2.84 degrees Celsius. So we don't want to find the delta T, we want only final temperature. So simply take this value and substitute with T2 minus T1. So we know our delta T comprised of T2, the final, minus T1, the initial. We've got the T1 and also delta T, so we can simply calculate our T2, which is 2.84 plus 18.24. Lastly, our T2 is 21.08 degrees Celsius. So this is our final answer for these questions. Okay, that's all for tutorial week 3 hour 3. We're going to proceed with subtopic 2.3 and 2.4 next week. Thank you.